Okay, last day. Last day. Last day of physics. Summer break after this. Oh, wait. In Australia it would be. Exam 5, that's all we have left is the exams. Exam 5 you can take either on Monday night at 6 p.m. in this room, or Thursday (12:15) at 2 p.m. in the room next door, 1328. So whichever one of those works better. You don't have to tell me ahead of time, just show up. And then for lab this week, for the people who have lab tonight, we're just doing that post test, the bubble sheet test. So it's just going to take half an hour or so. And then that's all. So we have one more topic to get through. We haven't done rotational kinetics yet. So we're done with rotational kinematics. So the last topic is rotational kinetics. And with particle kinetics, the main result was Newton's second law. So remember, particle kinetics the main result was Newton's second law. So F net is equal to the mass times the acceleration. For rotational kinetics, the main result, what we're working towards, is, I call it the rotational Newton's second law. It's actually derivable directly from Newton's second law. And I abbreviate it RN2L. Trademark. And this says, add up the moments produced by all the forces, so MA net is equal to the mass moment of inertia about that same axis times the angular acceleration. So that's what we're going to get to today. And before we can do that, we've defined angular acceleration, but we haven't defined moments yet, torques, and we also haven't defined the mass moment of inertia. So the first, before we can do that, we need to define the mass moment of inertia I sub A, and that's the rotational version of mass. And then we have to define the moment or torque. And that's the rotational version of force. So first I'm going to do the mass moment of inertia. And it's abbreviated capital I sub A. And this is just a measure of how hard an object is to get spinning, to get rotating. It's resistance to rotation. So a high value of the mass moment of inertia means that it's hard to rotate. And a low mass moment of inertia means it's easy to rotate. So an example of this in sports is like in diving, you get a lot of points for doing your dives like this. Put a bathing suit in there for modesty. And you don't get as many points for doing the same trick like this. So tricks this way, like to do a triple backflip this way, is hard compared to this. Well, this is also hard, but it's not as hard. I imagine it's. I've never done a triple backflip, but it looks hard. Okay, so what is it about this that's harder than this? Why is it easy to get your body to rotate in this position and not in this position? What accounts for the difference? Objects are hard to rotate if a lot of mass is distributed far away from the axis of rotation. If a lot of mass is positioned far from the axis of rotation. When something's moving, so this diver isn't attached to a joint of any kind. He's moving freely through the air. And so the axis of rotation is the center of mass. And so if you imagine the center of mass being somewhere in the chest, there is a lot of mass distributed far away, like the legs have mass positioned a large distance from the center of mass, whereas in this tuck position, if the center of mass is right here, everything's packed as tightly as possible in toward the center of mass. And that makes this have a low moment of inertia and this have a high moment of inertia. So that's easy to rotate, hard to rotate. So here's a demonstration. And people like this demonstration because there's a good chance I'm going to fall off and hit my head on that thing. So I feel like I owe you that after this hard semester. I'm going to do it right next to this sharp corner. Okay, so let's see. So if I get this going, I'm going slow, pull them in close, and I go fast. It's like magic. Isn't that cool? So it works really well when I'm holding these weights because, you know, my hands don't have as much weight as these do, so you wouldn't see it as dramatically. But this is basically like what figure skaters do, you know, when they're like, ah, and then they pull their arms in and spin super fast. Whoa. Okay, so that's mass moment of inertia. And we're going to do calculations for only one kind of shape. Let me do units first. So units for mass moment of inertia are mass times length squared. And so SI units are kilogram meter squared. Nope, it doesn't get used enough. It has to, you just have to deal with all the letters. And so for a rectangular shape, so let's say this rectangle has a length L and a height W, width. And let's say the axis of rotation is the center. So this is what I'll call A. The axis of rotation is at the center. Then the mass moment of inertia of the rectangle, and also it needs to have a mass of m. Then the mass moment of inertia about A is 1/12 times the mass times the quantity length squared plus width squared. How do I know it? Well, I probably know it from looking in a book, but you actually can derive it. The definition of this is an integral definition, and so that 12th comes from integrating something twice. I don't. For anyone who's had calculus, you know, like, well, you know, when you integrate, you get something in the denominator. First it's a 2, then it's a 3, then it's a 4. And when you're done with all the integrations, those have multiplied together to give you a 12. That's where it comes from. So that's how to calculate the mass moment of inertia if the axis is at the center of the rectangle. But sometimes the axis doesn't happen to be at the center. So if the axis isn't at the center, you use what's called the parallel axis theorem. And the parallel axis theorem says the mass moment of inertia about A is equal to the mass moment of inertia about the center plus the mass of the object times d squared. And that d is the distance from the center to the axis. Okay, so if you look at that term, the parallel axis theorem term, you're always starting with the value that you would get if it was rotating around the center, and then you're adding on this thing that's the mass times a distance squared. Can mass ever be negative? Can something squared ever be negative? Okay, so you're always adding to this, which means the smallest moment of inertia of a body is always if it rotates around its center. Anything that, rotating around anything other than the center is harder than rotating around the center. Okay. All right, so let's say we have this rectangle. The height is 1, and the width is 0.5. And the mass is 10 kilograms. So let's calculate the mass moment of inertia about A, B, and C. So first we're going to calculate I sub A, then I sub B, then I sub C. Okay, so for A, that's at the center. So the mass moment of inertia about A, that is the mass moment of inertia about the center. And that's equal to 1/12 times 10 times the quantity 1 squared plus 0.5 squared. I don't know what that is. So let's see. 10 times 1.25 divided by 12. It's a little over 1. 1.04. 1.04 kilogram meters squared. Okay, so that's what you would do if the pin or the hinge or whatever was at the center. So now let's figure out how easy or hard it is to rotate this object if the hinge or the pin was at B. So the mass moment of inertia about B is equal to the mass moment of inertia about the center plus 10 times, what's the distance from the center to B? 0.5. And so if you add these together, you get 1.04 plus 2.5, so 1.29 kilogram meter squared. Right? No? Oh, yes, that's way off. Dang it. 3.54. Huh? Any questions about that one?
Wouldn't C be the same?
C is a little farther away because,
You have to take the angle?
yeah, you have to use the Pythagorean theorem. If you think of this right triangle. Okay, so for C, the moment of inertia about C is equal to the moment of inertia about the center plus 10 d squared, and that d squared is equal to 0.5 squared plus 0.25 squared. It's half of the height and then half of the, horizontal distance. Can someone calculate that? .3125. And so the moment of inertia about C is 1.04 plus 10 times 0.3125. And so that's 4.165. kilogram meter squared. Any questions about those? Okay, so what that's telling you is if you put the hinge, the axis of rotation, at these three different spots, how hard is it to get this thing rotating? And this tells us that, well, what I just said before, that if the hinge is at the center, it's easiest to get it rotating. If it's at B, it's harder. And if it's at C, it's hardest to get it rotating, because that's the furthest from the center. Okay, so now we have to define the moment. Or the torque. This is, it measures how strongly a force contributes to a rotation. And so if you have an object that this is the candidate for being rotated, and this is the axis of rotation, and then a force is applied somewhere else away from the axis. So I'll call this point P. This axis I'll call A. And let's say that if you draw a line between where the force is applied and the axis, so there's a line between those two, that line is perpendicular to the force. That isn't always going to be the case, but let's say that that's the case for now. So let's say this is the force F. And those are perpendicular. So if the force F is perpendicular to the line between P and A, then the absolute value of the moment is equal to the absolute value of that force times d where d is the distance between P and A. That doesn't tell us what the sign is, so we need a way to figure out the sign. The sign comes from the direction of rotation. Let's say the direction of the produced rotation, or the rotation that would result. If that force would produce counterclockwise rotation, then the moment is positive. Yeah, it's a funny thing. Yeah, well, for us, everything, positive rotations have always been counterclockwise. Remember, like with cosine and sine. And the way it works, it comes from vector math. This way of multiplying vectors called the cross product. So that's where it comes from. But it does seem...
Seems like in the regular world.
Yes, exactly. Right.
Normal.
It's a nuisance when I'm doing like figures in Word for like problems and stuff, because I always think of positive as counterclockwise and everything, Yeah, anything else clockwise is sort of the default, but not here. So counterclockwise means the moment is positive, and clockwise means negative. The sort of intuitive description of what a moment means think about like a bolt that you're trying to turn. and you're trying to turn it with this wrench. And say that you have the capacity to apply 100 newtons of force. Where would you try to apply that force? Would you try to apply it here? Or here? Or here? Your best chance of turning that bolt is to get the force as far away from the axis of rotation as possible. If you know, no matter what force you apply, 1,000,000 newtons or whatever, if you apply it right over the axis of rotation, it'll never turn. All that'll happen is eventually the bolt will just strip, just rip right off the wall. This one, you could get it to turn, but you have to apply twice as big a force as you would if you applied it here. Okay, so that's the idea of a moment intuitively. You get more bang for your Newton buck by moving the force far away from the axis of rotation. And so let's think about it in terms of the axis and that point P where the force is applied. Okay, so you don't want to do this. You don't want to do this. You want to do this one. So if this is the axis of rotation, and the force is applied here, then the line between the axis and where the force is applied is this. So is that force perpendicular to the line between P and A? Yes. And the distance is the length of that red dotted line. Okay, so let's do an example. So let's say this is the object, and this is the axis. And a force is applied at the center of, let's say that's 200 newtons.
200 newtons going up.
Yes. And the radius of this circle is 0.1 meters. What's the moment, MA, produced by that 200 Newton force? Well, this is the point P where the force is applied. If you draw a line between P and the axis, it's perpendicular to the force. So that's good. We can use this equation. And the absolute value of the moment then is equal to 200 times, what's the distance between P and A? It's one radius, yep. So that's 20 Newton meters. Oh, I didn't talk about the units yet. This is what the SI units are. I'll get that in your notes. So that's the absolute value of the moment. And now, with the axis here, would that force make this object rotate clockwise or counterclockwise? Clockwise. And notice that where the axis is has an effect on which way it would rotate. If the axis was over here, that force would make it rotate like this, you know. But since I specified that the axis is here, that force makes it rotate like this, clockwise. And so MA is equal to negative 20 Newton meters.
Explain the rotation a little bit more, like
Yeah. Yeah, well, so just think we're going to always do this analysis one force at a time. So just imagine that this object is in a frictionless environment, like on ice or something. We're looking down at it on ice. And there are no forces applied except the one we're dealing with at the time. And the axis, imagine that being like it's spiked to the ice at that point. All it can do is rotate around that point. So if you applied a force like this, like imagine tapping it up with a hammer, would it rotate, which way would it rotate around that axis?
okay.
And that circle would loop around like this.
Okay, that makes more sense.
If that 200 was going down,
Yep.
it would be the same.
No, if it was down, it would rotate. Like if you tapped it down with a hammer, it would go this way, counterclockwise, so it would be positive. And that makes sense if you think about the wrench again. You know, if you want to loosen this, you want to get it to rotate counterclockwise. And so you know from experience that you want to pull down on it. If you want to tighten it, you want it to rotate clockwise, so you have to apply a force in the opposite direction. Right?
Unless it's left-handed.
Oh, yeah, right. That's a real pain.
So 20 Newton meters is not very much, right? That's
20
4,
Newton meters.
5 foot-pounds, 3 foot-pounds?
Foot-pounds. I'd have to, let's see, a Newton is about a quarter of a pound. And
Yeah, so 4 or 5.
yeah, not that much. But that's a pretty, I mean, it's 4 or 5, like 5 newtons is very small. 5 Newton meters is more like you have to turn pretty hard on a wrench to get 5 foot-pounds. Okay. Any other questions about that? So let me get the units in here. Units for a moment. Are always units of force times units of length. And so in SI units, that's Newton meters. In British units, that's foot-pounds. But anything that, any kind of torque wrench, you can measure torques in all sorts of different units. But what they all have in common is it's going to be a force times some unit of length. Okay. So of all the forces out there and all the axes out there, what percentage of them would you guess have the force exactly perpendicular to the line between the axis and where the force is applied? What percentage? 0. 0%. So that's a problem. I mean, that's rounded down kind of, but okay, so what if the force is not perpendicular to that line? You can do it like that. You're right, but that's not how I'm going to talk about it. So what if the force is not perpendicular to the line between P and A? Well, it turns out, without changing the problem, so here's a lucky fact. Without changing the problem, you can move the force anywhere along its line of action.
And the line of action is that dotted line Mr. Martin?
No, but I'll show you what it is. Line of action. So, for example, if this is the object and a force is applied here, you can pretend like the force was applied at any of these locations that along a line that's parallel to that force and goes through the place where it really physically was applied. So including all these points that aren't even on the body. It doesn't make physical sense, but mathematically it works. So for example, you could say that this force was applied here, or over here close to the middle, and it doesn't change the calculations. This is the line of action. So just move the force along the line of action and so what we're really doing is moving the point P where the force is applied. And do that until you're at the spot where the force vector and the line between P and A are perpendicular. Okay, so here's an example. Let's say the object is a rectangle that's 2 meters long and the height is 1 meter. And the axis of rotation is at the center. And a force of 20 newtons is applied at the corner. So what's the moment produced by that 20 Newton force? Well, this is the location P. And if you draw a line from P to A, it looks like this. And that line isn't perpendicular to the force. But the line of action is this. And so we can move that force anywhere along the line of action. And if you move it to this new location here, let me draw it again. So now we've changed the problem to be this. A is here. P is here now. The line between A and P is this, and it is perpendicular to the force. And so now the absolute value of the moment is 20 times the length of this line. So what's the length of this dotted line? 0.5. So that's 10 Newton meters. And now if you applied a force, so if this was free to rotate around a pin here, and you tapped it with a hammer this way at that location, would it rotate clockwise or counterclockwise around that pin? Clockwise, and so negative. So MA is equal to negative 10 Newton meters. And the negative is because it's clockwise. Any questions about that? Okay, so now we're at rotational Newton's second law. The rotational version of Newton's second law. This says that if you add up all the moments around the axis, so I'll call that MA net, that's equal to the object's moment of inertia around that axis times the angular acceleration. Okay, so let me do an example. So let's say that we have a board that's connected to the wall. It has a length of 1 meter, so from the end to the center is half a meter on both ends. And let's say this is the axis. And let's say, okay, so can you picture this? It's like a board that's anchored to the wall by a pin in the middle. If you apply a force to this end, it'll spin around the middle. And so let's say we apply a downward force of 10 newtons here and an upward force of 5 newtons here. Oh, I didn't give the end of the dimensions. So let's say that the thickness is 0.1 meters. And the mass is 2 kilograms. And we want to know what's the angular acceleration. Okay, so first let's do a free body diagram. There's the two forces that were given. There's a 10 Newton force here, a 5 Newton force here. And then there's also the weight. The weight is always applied at the center. So we have a downward force of 2 times 9.81. So 19.62. And so you can think of the moment net is going to be equal to the moment produced by the 10 plus the moment produced by the weight plus the moment produced by the 5. And so let's just do those one by one. The 10 Newton force, the absolute value is equal to, let's think a little more than that. If this 10 Newton force is applied here, is the line between the axis and where the force is applied perpendicular to the force? No, but where can we move the force so that it is? So if we move it right to the middle here, then the force is perpendicular to this line. Okay, so the absolute value of that moment is equal to 10 times the length of this red dotted line. What's that length? 0.5. So that's 5 Newton meters. And then we have to think about the sign. If you applied, so the axis is here. If you tap down with a hammer, would that make it rotate clockwise? No, that's counterclockwise or clockwise? Counter. So this is positive. Any questions about that one? Okay, so now the weight. The weight is acting at the axis, and so it's like that example that I gave of trying to turn a wrench by applying a force directly to the bolt. It's just never going to do anything. You end up with a distance of 0, and so the absolute value of this moment is equal to 19.62 times the distance from the axis to where it's applied, which is 0. So the moment produced by the weight is equal to 0. And then the 5 Newton force. The 5 Newton force is applied here. Is that force perpendicular to the line between where it's applied and the axis? No. But where can we move that to? Yep, just move it right to here. And then the line is perpendicular to the force. So the absolute value of the moment is 5 times the length of this black dotted line, which is 0.5. So you get 2.5 Newton meters for the absolute value. And then would that force make this rotate counterclockwise or clockwise? Counter. So that's also positive. So the net moment is 5 plus 0 plus 2.5, so 7.5 Newton meters. Those are counterclockwise. Yeah. Both of those two forces would make that rotate counterclockwise. Yep. Okay, so now we have to figure out the moment of inertia. The axis is at the center of this rectangle, so it's just going to be equal to 1/12 times 2 times 1 squared plus 0.1 squared. And so that's equal to 0.168, and then 3 is repeating. Kilogram meters squared. Any question about the moment of inertia? And so now we can put it into the equation, and it says 7.5, positive 7.5, is equal to 0.1683 repeating times the angular acceleration. And so the angular acceleration is 44.55 radians per second squared. So the angular acceleration is counterclockwise. Is this thing speeding up or slowing down? Trick question. Well, I didn't say anything about when these forces are applied. I didn't say anything about what the angular velocity of this board was, you know. And so if it was sitting here at rest when these forces are applied, then it's going to speed up counterclockwise. But if these forces were applied when it was spinning clockwise at, you know, some angular velocity, then we have a clockwise angular velocity, a counterclockwise angular acceleration, and that means that the rotation would be slowing down. Okay, so let me give you another, set up a similar one and see if you can think through this one. So let's take the same board. But now the axis isn't at the center, it's at the left end. So the axis is here. There's a force of 10 newtons applied there. Five newtons applied there, and then the weight is applied at the center. What's the angular acceleration here? Okay, so work together on that. Ask me questions if you get stuck. Yeah, everything's the same. The only thing that changed is the axis location. Okay, I'll go through this. So a free body diagram looks like this. I'm just going to put the 10 Newton force in the center there. The 5 here. And there's the weight, 19.62. And this time the axis is on the left end. So the net moment is that 10 is acting right at the axis, so that doesn't produce any moment. The 19.62 has a moment arm of 0.5. The distance is 0.5 from the axis to where the force is applied. So that's 9.81. And then with that weight force, if it was acting alone, would it make it rotate clockwise or counterclockwise around that axis? Clockwise, yep. So the 9.81 is negative. And then the 5 Newton force, the distance from where it's applied to the axis is 1 meter. The magnitude is 5. Would that make it rotate clockwise or counterclockwise on its own? Counter, so that's positive. I'm going to rewrite this as 0.5 times 19.62. And so if you add this all together, you get a net moment of negative 4.81. The height is 0.1.
No, it's not.
That's 0.1, the height.
Yeah.
Okay.
But my question is, when you have the 5,
Mhm.
like at the distance.
So the distance that we want is the distance from where the force is applied to the axis. So it's this whole distance here. 1. All right, and then we have to calculate the moment of inertia. That's different now because it's not rotating around the center. So the moment of inertia is equal to the moment of inertia about the center. That's the one we did before. Plus the mass times the distance from the center to our new axis. What's that distance? 0.5 squared. So that's 0.1683 repeating plus 0.5. And so you get 0.668. The 3 is repeating. And now finally, put it into rotational Newton's second law, and you get negative 4.81 is equal to 0.6683 repeating times the angular acceleration. And so the angular acceleration is negative 7.2 radians per second squared. And so this time, because, so in the first example, the weight didn't have any effect on the rotation, and the object rotated counterclockwise. This time the weight, you know, if you try to take I don't have anything like that, but if you try to take a long thing and hold it by the end, you know that weight is fighting really hard to make it swing down like this. And that's what's happening in the second example. Since the weight isn't acting at the axis anymore, the weight is trying to make it rotate clockwise to drop down, and it wins out over the other force. Okay. Thanks for taking my class.